So hello everyone. Today we are going to present this paper called Theoretical Limitations of Multi-Layer Transformer. This is going to be the main paper that we're going to present. And then to get some motivating examples of like what problem are they really trying to solve, we'll use this paper on limitations of transformer architecture. So this is our motivating example, like what are the root causes of hallucinations in LLMs? So basically transformer is an architecture. It can compute certain functions, it cannot compute certain functions. And there's a lower bound for this architecture. It has to have certain number of minimum parameters so that it can compute a certain task. So this is what this is what we need to do. And the thing is, people have already tried to prove lower bound on transformer architecture, but there are three major limitations. One, people have tried to prove it on one layer transformer. They have tried to prove on multi-layer transformer, but they assume certain conjectures. So there's no proof on the lower bound of transformer for multi-layer case without assumption of any conjecture or any information theory or whatever theory conjecture. And third, you see in the previous presentations we were trying to prove it, like we were trying to see whether transformer can perform the parity function task or these are the tasks that are not directly relevant to the intended use of transformer architecture. Like transformer is built for language, right? And the parity task, three-sum task, two-sum task, all these tasks for which people have tried to compute the lower bound of transformer, they are not, like these tasks are not directly relevant to the intended use of transformer architecture. So the tasks for which people have been trying to use are not really good. Not relevant to the intended use of transformer architecture. Do you have a question?
What's an example of a conjecture?
Basically, a conjecture could be if I would say that I assume that the transformer, all the functions that transformer can compute, like it belongs to, let's say, TC0 class, to circuit complexity class, and they would assume that.
Well, I think they would show that.
Yeah, but this paper mentions that those were assumptions which you make and then you try to prove the lower bound.
I thought usually the assumption is something like in complexity theory, we assume that TC0 is like not equal to P.
Yeah.
And so then if the transformer is a subset of TC0, then it definitely, under the assumption that it's not equal to P, it can't solve certain problems in P.
Yeah, exactly.
Okay.
Yeah. So this paper, the theoretical limitations of multi-layer transformer, they try to do it for multi-layer case, and they use a task which is relevant to the intended use of transformer architecture. So now let's see what that task is. So Arham will now talk about that task.
So let's see here. Basically, in the paper, they use some natural language processing task as a proxy for reasoning, and they generally say that it can be used as a sequential function composition, and reasoning can be denoted using sequential function composition. So just look at this example. It says that the father of Frederick Chopin was Nicholas Chopin. Nicholas Chopin was born on April 15, 1771, and then the basic query that the user asks is what is the birthday of Frederick Chopin's father? So basically, just to compute this answer, it has to compute two different things. For example, let's say if this is denoted as X, it has to first query who is the father of Frederick Chopin, and then based on that output, it has to then query what is the birthday of that answer that it gets from the first step. So basically, if we have X that is Frederick Chopin, we first have to compute a function, for example, like father of, and then based on this answer, it has to compute the birthday of, for example, let's say it's denoted in the prompt. And if we have these two functions, that is how we get to the final answer. Basically, this is like sequential function composition in the sense that you first have to compute this function, and then based on this output, only then can you apply the birthday of function and then get to the final answer. So this is an example of two function composition in that you have two steps, and you need to complete both those steps to get to the final answer. And this primarily is used as a proxy, and then throughout the paper they use this example, like this function composition for reasoning, and then they denote that how this is a difficult task for transformers. So basically, these are two different examples from the Papadimitriou paper, and they show that based on sequential function composition, let's not get into the example, but the correct answer was 6 years, and then when they query the transformers, for example, GPT 3.5, GPT 4, and BART, they get different answers, not the correct one. And same for this, even though it's just a yes or no question, they get different answers from 3 different transformers. And then this is used like to basically prove that L function composition or function composition is a difficult task for transformers to solve. And let's go through an example to like see how this becomes a difficult transformer, or like what's the underlying reason that a transformer may not be able to solve a sequential function composition task.
Can I ask a question?
Yes.
Is this about a learnability result, or is this
Where's the
about
volume?
representation result?
It's more of a representation result because we'll get into the number of bits or like how message passing works in transformers, and then we'll see that if it has a large enough domain, then it might not be able to communicate the whole information for that function that it has to compute,
Right.
and then it cannot solve it.
Yeah.
Can we increase
So
the
it's
volume?
also a little bit different than the results that were for TC0 and whatnot, the circuit complexity,
Mhm.
because those were, I don't know whether those results would imply any of this. Would they?
Well, if function composition was contained in one of the classes, then yes. But it's not a
But like,
decision
do we know
problem.
that? Yeah.
That's what I was thinking too. I don't remember what we know about function composition and like what complexity class it's in.
Yeah. Okay. So that's something to think about. All right. Okay. I don't know either.
Yeah.
Because, okay, so what is function composition in circuit language, right? It's like a weird thing. Somehow you have this knowledge of like there's this function and it's like discrete, like you have this domain and like from this domain you're mapping this element to that element, this element to that element, and then you are supposed to be able to compose 2 of those things. And so somehow the functions need to be represented by the circuits. I guess you should somehow be able to do that, but all right, anyways, let's think about it offline. Yeah.
Let's continue. So
Yeah.
because this is like an example of 2 function composition, let's see another example of 2 function composition and see why it might fail for if we have limited number of bits. So for example, let's say we have 3 different agents or 3 different players. One is called Xavier, the other is called Phi, and the third is called Grace. You can read this, right? Okay.
Yeah.
Let's say Xavier has a number x that it knows, and both Grace and Phi know the number as well. And basically the communication is like Grace can communicate with Xavier and Phi can communicate with Xavier, but they cannot communicate between each other. And Grace has a function defined as G, which goes from input domain n to an input domain of n. And Phi has a different function called f, which has the same input domain n and goes to the output domain n.
I
And
see
what
what-
Xavier needs to compute is like it has a number x, and then it has to compute g of x, and then it has to compute f of x. And this is like a 2 function composition task. Like, okay, and basically what the assumption is that communication between Grace and Xavier is free in the sense that it can communicate any number of bits, and it can like just communicate the whole function definition to Xavier. But then Phi is like something we're trying to minimize, and we want to know the minimum number of bits that Phi has to communicate such that we can correctly output f of g of x, right? Is like the situation clear, like what we're trying to solve it? Okay, so let's say that because this is free, let's say, and it already knows x, it can communicate the function, and Xavier can now compute g of x, right? But
Sorry,
then,
I have a question.
yeah,
Is the communications are like bidirectional? I mean,
no, that
How
doesn't
we-
matter, just unidirectional, so just Grace can communicate with this, and that has to communicate with Xavier as well. They already know the function, like x initial value.
so there is no
So
query like
Xavier
from
cannot ask a question of Faye.
Javier can or cannot.
No.
No. So it has to communicate the function completely.
Yes.
So yeah, like Faye, right, like cannot know what value the function is needed.
Yeah.
Yeah, so it's unidirectional. They know the initial value x, but now that g of x is communicated, it cannot communicate the value, so that could get the
I
function.
see.
So now they have to communicate the whole function definition, so that it can actually compute f of g of x. Because even though they know x now, because it's g of x, it doesn't know what g of x is. It has to communicate the whole function, right?
And does Faye know G? Does
No,
Faye
they
know?
cannot communicate between each other, right?
Right. It doesn't have any idea about the G.
No, it doesn't know what g is. It just knows what x is. But because we apply g of x, that becomes
I see.
transformed into a different domain. Yeah.
So is this setup motivated by anything in practice, or are we gonna get there?
We're getting there. Like, this is just preliminary things. Any other questions? Yes.
Because f and g lie in some sort of hypothesis classes.
No, it's just like a function from n to n.
Okay.
And we
Any
just want to-
function.
It says any function, but they're different. G and f are different functions. Like, that's the most important thing. And yeah, let's move. So let's see how many. What we're trying to do is minimize the number of bits that it has to communicate, so that it can effectively compute the f of g of x. So what happens is that because the output domain is n and the input domain is n, we have a total of n raised to power n functions that f of x can lie in, and we have to communicate this whole function class, this whole n raised to power n functions, to Xavier so that it can compute g of x. And how it will do that is basically it has to communicate f of 1 and then f of 2 and then all up to f of n. Like, this n represents like the input domains, and for each input it can have like n different outputs. So it could be like n bit, like it could be 1 up till n different outputs. And to communicate like output for one specific input, it would need like 1n, for example, log n bits. Like, for example, if n is like 4, it has to communicate up to 1, 2, 3, 4, and this can be represented in log n bits, which is like different 2 bits. So just for like one input, it has to communicate log n bits. So across n inputs, it would need at least n log n bits to effectively communicate the function, right? And if it is allowed to communicate n log n bits, then we can effectively communicate the whole f function and we can actually compute it effectively. But if there are any less than n log n bits, for example, if we do n log n minus r bits, then the effective rate of hallucination increases, right? Because we cannot effectively communicate. And what the underlying principle is, like the pigeonhole principle. We can go into a bit into that.
And we are trying to compute it exactly, right?
Yes, we need like the exact code. So what basically this means is that through the pigeonhole principle, like everyone knows about the pigeonhole principle, or should I go into that? Yeah. Oh, thank you. So let's say there are n pigeons. This is the pigeonhole principle, and there are example m pigeonholes. Basically, the idea is very simple. That, for example, let's say we have 3 different buckets, and we need to put a pigeon in exactly one of these buckets, right? So it says that if n is less than or equal to m, then we can uniquely put a pigeon into a single bucket, right? Like p of 1 can go here, p of 2 can go here, and p of 3 can go here. But if n it becomes greater than m, at least the fourth will have to either go here in this bucket, or in this bucket, right? And then it loses that unique identifier that you cannot communicate effectively, and these two will be colluded together, right? So in the same example, if we have like each bucket denotes like log n bits, like this is.
So wait, so the principle is that if there are more pigeons than pigeonholes, then there will be at least one pigeonhole that has 2 pigeons in it.
Yeah.
Okay.
Yeah.
Just to finish the thought.
Yeah. So yeah, the basic principle is that if there are n pigeons and then there are m pigeonholes, there would be like at least one bucket where at least this number of pigeons would be there, right?
Right.
Right. This is like the pigeonhole principle. In the same aspect, like if we have a bucket that represents log n bits, we would need at least n such buckets to contain the whole function class in it. But if there are any less buckets, for example, if we have 4 different, like n is equals to 4 and we need 4 different inputs, and we only have 3 buckets, then f of 1 can go here, f of 2 can go here, and f of 3 can go here, but at least f of 4 will be colluded together for 2 of these inputs. And then if the actual g of x value was, for example, in this, at least one of these f of 2 or f of 4 would be incorrect, right? If the output is different. then that function cannot be computed correctly. And this is like the underlying principle behind everything that we will go through in the lecture. And that is why we just wanted to focus on that, because it's the underlying proof that they use for the proof that a transformer cannot solve an N function. Yes.
I think maybe that thing is a little bit confusing with putting the f of 1, f of 2, f of 3 in the buckets. Actually, what's going in the buckets are all the different functions, right? So it's not the values of the functions that go in the buckets, it is all the possible functions. So if there are like 4 possible functions, f1, f2, f4, then f1 goes there. So you can't tell the difference between some functions.
Yeah. So for example, this was just for like explanation, but if there are log n minus r bits, then the whole function class cannot be correctly contained within this many bits, right? Because we just said that n log n bits are required to correctly contain this function class. Then if we have any less bits, our rate of hallucination will increase, because we cannot express the whole message in limited set of bits. Any questions? Any confusions?
You're just trying to prove that the communication cost is analog n.
Yeah.
I think you're getting it. Okay, so till now we basically talked about an L function composition task, and these, you see those examples, they are basically like in language we have written those, and they represent some sort of N function composition, and transformers have to be able to like understand and solve this task to be able to answer those kind of questions correctly. So now let's move on to the theorem that this paper basically, this is going to be the whole bird eye view of the presentation. So they say that there is no deterministic autoregressive communication protocol, like there's no autoregressive communication protocol that can solve this L function composition task if we have two conditions. One, our layers in the transformer are L, and we have fixed number of bits. So so this is what we are going to prove in the whole, not going to prove, like we are going to tell you the main components that the authors use to prove this lower bound on transformers. So right now you get an idea of what an L function composition task is, and I'll talk about it now in more detail. It's mathematical stuff. So we'll first discuss the L function composition mathematically, and then we'll talk about the autoregressive communication protocol that the authors devise in the paper. And we'll talk about the autoregressive communication protocol. And finally, the authors prove lower bound on this autoregressive communication protocol for this task, which is L function composition task. And they use a technique called indistinguishable decomposition in their proof. We'll talk about that technique. So there are three main things that we're gonna discuss in the rest of the presentation. Indistinguishable decomposition. So let's first understand the L function composition task. Yeah.
Why do we care about why do we care about autoregressive communication protocol?
Yeah, we'll come to that. Yeah, basically they prove this whole thing for decoder only transformers.
Oh.
Yeah. So
this is basically a simplification of the transformer network that you use, and then they use that to prove the domains, and basically the indistinguishable decomposition part, the pigeonhole principle is like the underlying definition for that, and then they use that to suggest that domains are large enough so a transformer cannot communicate it effectively, and then we'll go into
we'll talk about each of these components in detail. Let's first discuss the L function composition. So
Clarification question.
Like, what does this theory tell us? Like,
clarification
why would you care
question.
about this theory?
Oh, sorry, try. You go first.
yeah,
Why
so
would you care about this theory? What does it tell us?
it's basically telling that if you have L layers and if you fix the bits in that transformer, you cannot compute a task, which is L function composition task. You need to have more. So this is basically fixing a lower bound on the.
And because
Yeah, I guess the reason we don't understand the theorem is because we don't understand this communication protocol thing. Unless it's defined, we won't understand what the theorem says. But let me ask a clarification question before you go there. So is the theorem going to be relevant for chain of code, chain of thought kind of computation, or it's a one shot? Chain of thought.
So they have a corollary for chain of thought, and they also.
Oh.
Yeah, we'll talk about corollaries in discussion.
like the theorem is not related to chain of thought, it's just like a direct answer, but then they have some extensive parts later, and then they go into
But
chain of
in
thought.
layman terms, the theorem eventually, you want to prove something like that if you have an L-layer transformer, such that, I don't know what is B bits, like something is represented only with B bits, you will clarify that. Then you cannot, like, you will eventually find some function, like L functions, such that, okay, well, you cannot represent all the different combinatory many function compositions on n elements if you have L functions that you're composing. Eventually, this is what you're trying to show, right?
Yep.
And there is no chain of thought here or anything like that.
No.
There's no chain of thought decoding. Okay, good.
Yep.
And then, okay, so I didn't understand this B bit part, but maybe you're gonna.
Yeah,
clarify
we'll come to
it.
that. So we'll come to that. Whatever is related to transformer, we'll talk about in the part 2, autoregressive communication protocol.
Okay.
Yeah, so, okay, let's move on to the L function composition task mathematically. I'll write it as L. So we'll denote it by L, and this is what the inputs to this task are. So we'll define some inputs. So there will be a query to this L function composition. There will be an initial input, and there will be some more functions that we have in this task. So let's say up to L. So let's see what each of these are actually. So Z0, which is the initial input, is basically element of M, and Z1. So I'll write a general expression for all of these functions. So remember that these are all functions. These are not like normal inputs or something. These are functions. This is the initial input, and this is a query. So each of these functions, what is the input domain of them, and what is the output domain? Let's write that generically. So it would be ZL is a function from NL minus 1. I have not defined what it is. We'll go to that. And it also outputs in NL minus 1. So all of these functions, they are represented as this. And this initial input is element of this. So what's NL minus 1? So let's write a general expression for NL. So NL is basically M multiplied by so there's initial some number, and it gets multiplied L times to some other number, and this is basically NL. Like initially you have, let's say, M, then M multiplied by N1 would give N1, and M multiplied by N2 would give N2, and so on. And here L is element of so if I expand it, so what would be N0? N0 would be M, right? What would be N1? N1 would be M multiplied by N1. What would be N2? It would be M multiplied by N2, and so on.
This is like M, N2, and 1.
No, wait.
N1 and 2.
N2 should be
N1 times N2.
It would be
M.
N1 into N2.
Oh yeah, sorry.
Okay.
Yeah. Okay. And yeah, so you multiply it. So basically this is a bigger input domain and output domain. This is a smaller domain. This is a smaller domain. So so you basically get the point that these are L functions, and each of these functions, as we go on, the input domain increases and the output domain increases.
So Ni is natural number. Natural number.
Yeah. So now that
This is sort of weird. Like, is there a motivation to do things this way? It seems that you're playing with the size of the domains as well. I suppose that the domain can stay fixed, and why not?
So when we'll actually apply the L function composition thing, like initially you would have M input, and then you apply one function, and then you next function, apply next function, and you add in queries, the input domain would keep increasing. I think this point will get cleared if I do the next step. Just like,
Yeah.
Okay.
yeah. So let's try to understand what is W. So till now we see what the input and output domains of the functions are, what is the initial input, and W is basically a vector, query vector, and it has multiple queries from N1. First query would be from here, second query would be from here, so it's element of. So this W, which is the query vector, would be element from this product set. So now let's actually see how the L function composition task works, and then you would know why, like the input domains and all
I
these.
see. Okay.
Yeah. Okay.
So shouldn't the range be an L?
Just wait for the example.
Yeah, just wait for it. Now
Okay.
we're going to do the example. Yeah.
Sorry.
So initially we would have.
I guess we do this for the sake of Trinity or something.
Yeah. So let's see the example. Initially we would have Z0, which would be element of M, and then we would compute the first thing I0, and it would be, so I0 is just the input, and it is element of M. Then the next thing is we compute I1, the next thing in the function composition, and it would apply this function Z1 on this input I0. So we know that I0 is element of M. So the input domain of Z1 is here, it's M, and we know that Z1 also outputs in the domain of M. So Z1 would also output in the domain, and this would be element of M as well. So if you look back here and try to see what is I0's domain, it is M, and Z1's output domain is also M from that formula.
Sure.
So this is the next step. From here we start taking in the queries, and from here the input domain like increases and the output domain increases. So let's see. So this is Z2, and we take in I1, and we take a query called, let's say, W1. I1 we know is element of M, and W1 is from here. It is element of N1. So the input domain of Z2, you see, it's M multiplied by N1. So there can be M multiplied by N1 different possibilities. So because there can be these many different possibilities, the output would have M multiplied by N1 different possibilities. And we can also write it as N1. So I'll do one step more to make it more like clear. So these are different steps in L function composition. So first we are computing one function, then using that function to compute the next one, using that to compute the next one. So let's compute I3, and I3 would be, we apply Z3 on some two inputs. What are they? One would be this I2 from previous, and one would be the next query. So it would be W2. I2 we know is element of N1, and W2 is element of, so from this thing.
Right.
And so you see the input domain is now like increased. There are N1 different possibilities of I2. There are this small N2 different possibilities of W2. So there would be more possibilities of output, and this output would be element of N2, and it keeps increasing. So let's write generically. So what would be IL? Which IL is going to be the output of L function composition task, and it would be ZL applied on previous function output IL minus 1, and the weight matrix or query WL minus 1. So, and this is going to be element of N L minus 1. So if I revise it, this is the L function composition task that is going to take some initial input, that is going to apply multiple functions on this input, and at each step it would be taking some query to keep progressing towards the next function. And what is the input domain of this initial input? It is element of M. There are each of these functions input and output domain keeps on getting increased, and that increase is defined by this function, and the query W is an element from this product set. And when you keep applying these functions at each depth, eventually you will compute L function composition for the given input query.
I guess just one note, like if you look at I2, then the input to Z2 is actually like the bracket M Cartesian product with bracket N1, which has M times N1 elements, which I guess we just one-to-one map to the set bracket M times N1.
Yeah.
It just might be a bit, yeah. And the Cartesian product. Yeah. So those are the actual input domains, but then we just map it to numbers of the, okay.
You wrote the
Okay.
query vector is a dimension of, like, it is an element of the Cartesian product of N1 to NL, but you're only using the WL minus 1.
Yeah, it should be L minus 1. Thank you. Thank you.
Yeah.
Okay.
I guess we will see the purpose of this soon.
Yeah. So yeah. So till now we have formalized the L function composition problem and what it is, and now we are going to move forward to the autoregressive communication model that the authors write. And yeah, so Arham will talk about that.
Okay, so in general they use a simplification of a transformer network, and the autoregressive communication model is basically how a transformer would work, but they have some kind of different notation. But generally how they define a transformer is that a transformer contains something like H, D, P, and L, where H is the number of attention heads in a transformer. Sorry for my writing. The D is like the dimension of the attention embedding, for example like this, and P is the precision for the embedding. For example, it could be float 32 or float 16 that is used.
Sorry, I'm a bit confused over this. So you wrote NL is M dot, yes, and then you are doing a Cartesian for N1 is equal to M cross N1, and then over there you have a set. So
Yeah. So this is not a Cartesian product. This is normal product.
okay.
So each of N0, N1, N2. So N0 is the input domain of this. So it is some set of natural numbers. N1 is the input domain of this bigger set of natural numbers. So for each of these next functions, the input domain increases. Why? Because one of these queries also comes into the function.
I guess just like there's a bunch of right things on the right hand side that need brackets, like the M's and the
I think so,
N2s
too.
and the NL1.
Yeah, I think I'll
Just
just do that.
if you want. Like all the element of, right.
Yeah, I think I'll change the color.
Yeah.
Yeah.
No, those are fine.
Yeah.
Sure.
And on the right, like the N2, the NL minus. Just, I'm just assuming that was where the question was kind of.
Yeah.
yeah.
It's also if you want to be consistent, the times to your left should be dots.
Yeah.
Like those times, like you're saying N1
Yeah.
equals to
Those
M
should be
times
dots.
N1. They should be dots to be consistent.
Yeah.
Yeah, the way you defined NL has a dot, and then the way you wrote it
If
has
you can
X.
change the
Oh,
cross
yeah,
into
so
the
you want me
dots.
to put
Yeah.
dot here?
That's
Yeah.
okay.
Well, like that's how you defined NL, right?
Yeah.
I don't know.
I think this is all very clear.
Okay, let's move to the transformer.
Yeah.
Sure.
Okay, yeah. So a transformer is defined using this, and P is like the precision, which could be like the number of bits each dimension is in. And then the L is the actual number of layers in a transformer. So they define that the total number of parameters in a transformer would be something like L into a polynomial function of H, D, and P, which is like, this is like one attention layer, and this is like the number of parameters in like one attention layer or one layer of the transformer. And then because we have L such layers, and the total number of parameters in the transformer would be something like L into polynomial of HTP, which is like the number of parameters. And in this case, we're only talking about decoder-only transformers. And an important distinction that they put in the paper is like a small versus a large transformer, which is like a main thing, because then they say that they only focus on small decoder-only transformers for the proof of NL function composition of the theorem. And the definition is that for a small transformer, the number of parameters that is like defined as HDP or DHP, it's like something in which is less than or equal to n or the small of 1, where n is the context length or something like the length of the prompt, that is. And what this basically says that because it's like something less than the polynomial powers of n, and what this basically means is that the parameters in a transformer, parameters of a small transformer do not increase polynomially with increasing context length, which is like if we have like 100k prompt length or like 200k, the polynomial increases, like the increase in the number of parameters of one layer is less than the polynomial, that the increase in the context length. And for the large transformer, they say that DHP has to be greater than n raised to power epsilon, where epsilon is greater than 0. So basically what this means is that for a small transformer, the number of parameters do not grow polynomially. So we only have like polylogarithmic parameters with increasing context length. And then this is how they define for small transformer. And then in like the later proof, it only talk about small transformer, because intuitively I think it makes sense, because all the transformers that we have like fixed sizes, and generally the transformer parameters do not increase with like increasing prompt length. For example, if we have a small prompt or like a very large prompt, the transformer length or like the number of parameters stay the same, just the context length of the attention layer, it just changes with the sliding window, right?
So for this function composition problem, what is the role of the context window length?
So the prompt is defined in the prompt, like the functions itself are defined in the prompt. For example, when they actually query the input, like the query the transformer, what they say is they'll define the ZL function in the prompt, and then they'll define the ZL minus 1 function up till Z0, and then they'll define the actual query inputs. And what this means is that if we have a large enough domain, because ZL increases, like the context length increases a lot because with increasing domains of functions. So what this means is that if we have large enough domain, the number of parameters do not increase. We have like a transformer of the same length, whatever the function domain is or whatever the queries are. And this is how
this is more like the in-context learning kind of thing, that you can't in-context learn with transformers the composition of L functions unless the transformer is big enough.
Yeah.
It's not the same thing as what I was thinking about, that you cannot even represent the composition of L functions with a transformer unless the transformer is big enough. They're kind of different things. Of course, well, I guess it's very different, because here you're communicating to the transformer what the functions that you want it to compose are, and then you're expecting them to do the computation of composing the functions. In the other case, it would be like, can I set the weight such that after I set the weight, and I should be able to set the weights for any functions, the transformer implements the composition of the functions. It's very different.
So the task is generally defined as such, because whatever the function is, they define it in this specific sequence. So the last function is defined at first, and then the queries are specified at the end of the prompt. And then even though they do not show such empirical proofs or any examples of doing so, they just specify the task as such. And this makes sense because in general, Z0 and Z1 is applied first, and then Z2 is applied next. So they define it in this sequence, like the last function is defined first in the prompt, and then the queries or like the initial prompts are defined at the end. And this is
It's kind
how,
of also about like how expensive it is to reverse something. Like a precursor of this result, a simpler result should be that in order to be able to reverse a string without writing out intermediate results, you need, I don't know. Well, that makes no sense. It's, yeah, okay. That makes no sense, what I'm saying. Sorry. But it felt like that the reverse order is actually something that's important.
it'll
And
become
again,
important.
it is like trying to set the weights of a transformer that can compose functions given as part of its prompt, which is very different than what I originally thought, which is that in the training data, you have these functions that define that, oh, like this famous person's mother is such and such, she was born at such and such date, and like then you are asking these questions, but, and then the question is whether you were able to load it. This is more like, yeah, like the transformer, can it actually, when the functions are given as part of its input to the function composition. Yeah, okay. Different task.
I guess the example you gave is not exactly mapping to this
No,
now,
it's
like you
not
said.
exactly mapping, it was just like a
Yeah.
preliminary to what function composition is.
I mean, you
But
could,
kind
you
of
could
think
like
that if
easily
it ha-
imagine like listen, like this famous person's mother is this, and that famous person's mother is that, and so on and so forth, and then listing the date of birth, and that's part of the input, and then you're asking like, what's the date of birth of this famous
Right,
person?
but that's not a, like, that's, the input doesn't give you the functions. It gives you one of the input and output mappings of the function, I guess, or
Yeah, it
something.
was just a
Yeah,
basic example, but so
input.
let's say if they
Yeah.
had like multiple example of people and it provided like the relationship of all the people and then the birthdays
Yeah.
of all the people, that kind of defines a function in that way.
Yeah, yeah,
And
then it would be
requires a
fine.
query, but the only
Yeah.
example we could show like living
Yeah,
yeah.
but kind of think it in that sense, if this was two different functions and all of the input space was defined.
So
and then
when
we
they're
have to
talking
query.
about that experiment that it seems that transformers are unable to do this, do they actually mean that like this function composition when the functions are given as part of the input?
Mhm. Yeah.
Okay. So it's consistent with the rest of the picture. Okay.
Wait, so the experiments actually give like this whole
There
function
are
mapping?
no experiments. It's just a theoretical proof and.
Oh, but I thought they cite papers that do this type of experiments, no?
I don't know.
But you said that like
Yeah, you said
people
ChatGPT and
point
stuff at the
to
beginning.
examples
That
where
was some
transformers are
examples in
failing
the-
to do this thing.
Right. We didn't hear you, so.
Oh, like you mentioned that transformers actually like real life transformers fail to do this task, but that was not this task, then? Or we don't know.
No, this was the task that it was failing to do.
But then they actually run this, or
No, the initial examples that we showed were from the Baba Dimitrio paper, which was different, and then all of this is from the other paper.
I see. Yeah. Okay.
Yeah, there are no
Okay.
empirical proofs of this in the main paper.
Okay.
Like any confusions with this, because then we'll try to prove. Yeah, Roshan.
Also, like this proof has almost nothing to do with like the neural network, right? The weights or the representation ability. It's just an information theoretic bound. Because when you have causal attention in the transformer, each unit sees one token of input and it needs to somehow send that to some other tokens. And that communication channel has a limited number of bits. So it doesn't even matter like what you do with your training or the representation power of your network or anything like that. It's just that because the different parts of the network cannot communicate with infinite precision, you just have the information theoretic bounds.
But isn't that dependent on the architecture?
It's
but-
dependent on like we've specified like DHP is like the number of bits of the attention layer that can communicate, and basically the B in like the main theorem that we had is kind of represented in DHP, which is like if we have only these number of bits, can we communicate like the whole function? For example, in the initial phi Xavier example, if we had n log n bits, or if DHP equal to n log n or greater than that, then we would be able to communicate the whole function. But if the attention layers have very limited number of parameters in the case of small transformers, if DHP is less than n log n, we cannot basically communicate the whole function class, or because the function is defined here and it does not know W, because the decoder only setting will kind of go with that. But because now we do not know these, we have to communicate like the whole function domain to the output, or like the last token. And because we have very limited number of bits, we'll see how this relates and why in the limited setting a function might not be able to compute it correctly.
And maybe you'll say this, but it's important that it's ordered in that way, the input.
Yeah, it's important because now in this setting, because the queries are here, and we'll go over the autoregressive communication model now, it will become important because only these, like the last tokens, we're on the decoder only setting, only like we can only look at causal attention, so
Yeah.
only previous tokens matter.
Mm-hmm.
So like the B in the main theorem was like the number of bits or the message bits, and these are like constrained on like the size of the transformer, which is like DHP, and that defines the number of parameters in a single attention layer.
Mm-hmm.
Right, so the
It's
requirement
like,
is
maybe
that-
you should say number of bits or something, right?
Yeah. B is like
And
the,
so it's basically the argument is going to be that it doesn't really matter what the transformers are actually computing. This is how much storage they have
Yeah.
for like up to computing this much, and that storage is not enough to represent the whole function that was supposed to be sent.
yeah,
It's basically like summing up the number of bits required to represent all the information that will be needed at the very end. And if that sum of the bits is less than, if the sum of the bits required is more than the number of bits available, then you cannot do it.
yeah, that's like the main argument.
I see. Okay.
But so this only holds for n large enough, right? It's more like asymptotic.
Yeah, that's what the main argument would be, and that is why we established the domains here, because once we go there, we'll establish, the proof basically highlights that once this domain becomes large enough, and we have very limited number set of bits, we cannot effectively communicate in like very limited information.
But this is not an asymptotic bound. There is a particular number, and if you're bigger than that number, you can't do it. So it's not something that holds as the n goes to infinity.
But let's say DHP is like 8 billion. It's a small language model. We can still have a very large context size.
Yeah, but it has finite length. So as soon as you go bigger than that, you can't compute this task.
Very good.
Okay, so let's finally come to the autoregressive communication.
Yeah.
Yeah. So there Arham basically mentioned some preliminaries for transformer, what is HDP, and we are working with small transformers, right? So now let's actually see the autoregressive communication model that the authors built. So they'll represent transformer in their own model called autoregressive communication model, and what happens is, just like in normal transformer, we have like at input layer, we have multiple tokens going into the transformer layer. So in this model, the nodes where these tokens go in, they call them players. So this is layer L is equal to 1, and these are n, let's say, players. And each of these players will take an input. So imagine that input is a token. So this player will take input x1, this will take x2, this will take x3, n minus 1, and this will take xn. And we are currently at layer 1, and the inputs are like coming from the previous layer, so we call these inputs as, let's say, 0. So this is one thing. So we know that how the tokens are getting into the transformer. Now let's see how the tokens communicate, how the layer, how this thing here would get information from all the other tokens. So the way they do is, this player will send a query to all other players. So let's denote this query by pi 1, 2. Like player 1 sent a query to player 2. Lambda. So, and we are at the layer number 1. So this is all happening on the layer 1. And
Let's go.
this player sends query to, let's say, 1 sends to n minus 1, and 1 sends to n, and we are at layer. So each of these, so you see, this player would be, basically when this player sends query to all the previous players, it will get information from all these players. So this has information of all the players which are previous to it, and 2 would have information of all the players which are like behind it, not from this. So this is just like autoregressive communication model. In transformer, this does not know about what is ahead, it only knows about what is previous. So let's look at just this one player. This player 1 queries all the previous players, and all these players will then send something back. So
I have a never mind.
So let's say this is what player n sent back to player 1. Let's call it pi. And it is what player n is sending to player 1. And this thing is what player n minus 1 is sending to player 1 back. And this is layer 1. And this is what player 2 is sending back to player 1. And this is layer 1. So now player 1 is getting information from all other players, but it needs to somehow compute, like somehow make one final output of it, so that it, just like in transformers we do weighted average on all the values that come back. Here, what the authors basically do is, so this is an input that also is coming here, and this operation would happen. So x1 for play, so this is the player 1's input to the next layer. So this is what is going to be here. And how this is computed is, it would take the player 1's input at the previous layer, and it would union all the all the keys that come back, and all the keys that come back to player 1 from all other players, and it would just sum those. And what is j? J here is greater than 1. So j is greater than 1. For this player, like the information that it is adding here would be greater than 2. So NL minus 1s would be unionizing like this input and all the values that are coming from all the inputs greater than that particular input. So again, if you look at this equation again, so the thing that player 1 is computing is the original input of the player 1, and all other players are sending back some information to player 1. This is comma.
Okay.
Yeah, to player 1, and it just takes a union of all of that, and they don't define the union thing. Like I don't know what exact operation it is, but they just do union of all the information, and this is what is like getting computed. And the same would happen for player 2. So let's say this is player 2. Its output would compute as this, and for all. So this is just like transformer. Like you see, at every step or every token gets like computes its attention from all the tokens that are behind it, and it produces an output.
Why is the indexing from n on the left and 1 to the right?
Yeah,
Is that just how the
the
paper
same.
did?
Why not?
This is in the paper,
Yeah.
so just to be consistent with the paper, like we just wanted to be like that. So
Okay.
yeah.
All right.
And eventually what will happen is, so this is, we are playing around on the player layer 1 or the epoch 1. And so this was, let's say, layer 2. Okay, And eventually what will happen is we'll reach out to layer L. And this is layer 1 here. This is layer 2. This is the Lth layer. And eventually this model, at the end of the Lth layer, this player will compute the L function composition of all the inputs that we initially give it. So at each layer, like after the L epochs of communication, this L function composition would get computed. How this like L function composition scenario, like these inputs like come here, how this thing is like, we'll talk about that. But you understand the autoregressive communication model that each layer has some players, number one. All those players communicate together by some mechanism. We established that. This was the second thing. And the third thing is this whole thing happens for L epochs. So these are the three main concepts in the autoregressive communication model.
So there are two different kind of uses of L's here, right? One is the number of layers in transformer, and one is the number of functions in it. And
Yes.
Are those L's, do they have to be the same? Like,
No, and yeah, they have to be the same in this case, because the whole point is that if we have L function composition, and that we have 1 to L function, and we try to do it with an L layer transformer, we cannot do that task.
And if it's L plus 1, it works, if I remember, or something?
Yeah. So, yeah. So this is autoregressive communication model. Now let's see how this setting applies here. The L function composition setting.
I'm a bit confused with that union thing.
Okay.
Is it like the output is not a set? It's a token again, right?
Yeah, it's not defined specifically, and we were actually
No, just think about that it's aggregated information. We're gonna count bits.
Yeah. So basically what happens is, you can imagine that this input will be a d-dimensional vector or something, let's say.
Yeah.
Then, like there would be, this would be a vector, these would be vectors. There are limited bits. D is limited, H is limited, P is limited, and yeah.
It's like whatever operation you do, you can only represent the result with that many bits. That's what we're gonna use. That's why they don't care about what this union operation is.
Yeah. So all of
They
this.
just want some notation so that you can represent the calculation that's going on in the transformer.
It can be anything.
And it will not matter.
Yeah.
It won't matter, that's why probably they did not define it, but in a transformer it would just be aggregated together.
I see.
Because the
All that-
dimensions remain the same.
Yeah, all that
Yeah.
matters, you have to be like careful that this pi and like the queries lambda and the
Yeah.
values pi, they have limited bits. So
Yeah.
if this thing is querying all the other players and all the other players are returning some stuff, if the bits are limited, then all the information present here might not get communicated to this player.
Yeah.
Yeah.
So,
Can we think about like how you would solve this task without a limit on the number of bits? That should be easy, right?
yeah, then it should be, I guess, easy because you can just communicate everything in the first layer.
Yeah. Like in the first layer, you would just like push all the information that's available at the position, and then the last guy would have all the information. And since the computation otherwise is not limited, it would just do the computation, right?
Yeah. Also, in the preliminaries of the transformer, we mentioned that this paper assumes that all of this work is with small transformers. So this is why the bits are limited. If you don't limit,
And the smallest was like that the transformer doesn't grow with the.
Context.
Yeah, it's kind of a weird thing because I always think about a constant size transformer anyways. So
yeah. Okay.
right, but
I mean, it can grow logarithmically with it.
Yeah, that's
it's more like it's maybe better to interpret the result in such a way that if your input length is such and such, then if your transformer is not too big, then you're kind of doomed,
Yeah.
right?
Basically.
Like it's polynomially sized transformer. Then okay, like for some big enough input, you run out of bits and you're doomed.
I think Roshan is.
Because a constant could be big, but like it's gonna be a precise calculation, I think.
Yeah, in Java, there's another thing which is that it also depends on the number of layers. So there's this sharp separation that if you keep everything the same, the number of bits the same, the precision of everything the same, but if you go from L layers to L plus 1 layers, then the task is solvable. Right? So I don't quite understand that bit, but like, so it's not just talking about whether you can do something in one layer or not. It's also talking about the communication that happens over machine.
So this is like the main theorem of the paper, that an L layer transformer might not solve it, but then they have some corollaries that we want to discuss later. And one of that is that for the same task, if we just add one more layer, then the task is solvable. And there's no strong proof for that in the paper. And it's just like one paragraph of corollary, so I'm not sure how that is, but yeah, we just wanted to have a discussion on that later.
Okay.
Okay, so this is the auto-regressive communication model. Let's see how this setting applies here. So there will be 3 changes. One is they mentioned that these inputs, the inputs there were Z0, Z1, Z2 up to L, and here let's specify that. So in this case, first of all, let's change the naming of these players.
From 1 to
We'll add 2 more players.
Okay.
So, in fact, one more player. No, 2 more. Yeah, 2 more players. So this is player 0. Initially, we only had 1, 2. So we added a player 0, and we added player -1. And at the end, we'll have L -1 and L. So the same number of layers we have in the transformer will have that many players plus 2, so L plus 2. So why? Now let's see what each of these players takes in. So this will take in Z1. This will take in all the definitions of Z2 in the input. This will take in all the definitions of ZL -1, and this is going to be ZL. And here, this is going to take in Z0, and this will take in all the queries. So we increase the number of players, and each player is taking input at the first step, and this is basically the inputs of all the L function composition tasks. And at the end, now this player -1 should compute the L function composition of all the initial inputs. So I'll remove this thing. After L layers, after L epochs of communication, this first player will communicate, will compute L function composition output. So this is what we want to do. So I made 2 changes. One is we changed the numbering of the players, and secondly we clarified how the inputs will look like when we apply the L function composition thing here. So let's change the player names here as well. Okay. So now I want to establish why the theorem 1 says that if we have L layers and if we have B bits, we cannot compute L function composition. This is the final thing that is, and this is called indistinguishable composition. So try to see here. This is the L function composition output here. And to compute this L function composition output, we need these 2 inputs, and we need to apply this ZL function, right?
By the way, so W has its components, but it's just shown on the last position, or
Yeah, that's like a simplification that they do, so that the whole function definition is defined, even though it might be many more tokens in a transformer. In the autoregressive model, they just made a simplification that all of that function definition becomes just 1 token or 1 player. And the same for the query, they just say that in the communication model it's just 1 token, so that everything can be pay attention to at the same time.
So, but it's not quite all of the function because the actual function is also determined by one of the things in W, right?
Yeah.
Like the identity of a function is determined by Z and one of the components in W. And I guess for the proof, it's important that that information is sort of off to the side, right? Like if you split up W into pieces and attach each piece next to each function, would this proof?
Yeah, the W's are all here and they are defined in just one single token and they're at the end.
Right.
Like that relates to that part here because they're defined in a prompt in that way, so it becomes like whole function, like ZL becomes that, and the parameters or the queries, they do not have access to that, so the whole function has to be communicated to this last player over here.
Right. So that's kind of weird, right? Like the whole thing is hinging on the fact that the entire definition of the function is not just there in one place. It's split between the last player and one of the other players.
Yeah.
Yeah.
I
So this is like how they define the L function composition task itself. Like at each
Sure.
step you are getting a query. So yeah.
I didn't get the weirdness that Roshan is talking about.
So I guess I guess I didn't quite say something. So the way I'm thinking of W is that each function is actually a family of functions, right? So Z0 is defining not just one function but a family of functions with an extra argument, and that extra argument is like whichever component of W it is. So Z0 has two inputs, which you can think of as one is a subscript and one is the actual output of the previous function. So you actually have a composition of different parameterized families of functions, and then the W is telling you the parameter of each function, right? So actually the identity of the function is kind of split between two pieces.
Yeah. I see.
So you pass all of that information into like one token. Also, like, is the input length the same as the layer depth? The number
So
of
we
layers?
have
L
L
plus
players,
2.
and the number of players would be L plus 2 because they're like 1 to L functions would be L tokens, and then the initial query and the W is defined as two different tokens.
So like, okay, so you're roughly the same order, like your input length is roughly the same order
Yeah.
as the number of layers.
So I'll take the purple. So here you see, to compute this L function composition, you need these inputs and you need to know the definitions of all these function assignments so you can actually get an output, right? So here, this means we need to know what is ZL and we need to know what is IL minus 1 and WL minus 1. So the thing is, this is the input that is coming from the layer L minus 1. So we have this information, but we don't know if we have all these assignments, they are present here. So see this is the input to the last player, and it sends query to nobody. Nobody sends information to this player, and this thing just gets progressed till here, Z, L, like this. And the thing is, now when this player communicates queries to all the players next to it, and it tries to get the definition it needs the definition of this ZL so that it can apply it to the inputs that it is getting to get the right output. But the thing is, the authors say that if we limit the bits of communication to, because you see, this is the value that is getting back, this was the queries. If you limit the bits of these queries and values, you won't be able to transfer this ZL back here. And if you don't know the complete input to output assignments for ZL, for some inputs, this L function composition output won't be right. So this thing, they call it indistinguishable decomposition. You cannot distinguish certain functions so that you can compute the L function composition task. So this is sort of the whole gist of the proof, and they use this technique in the proof to prove the initial theorem, which was that if you have L layers, just like that, if your communication bits are fixed to HDP, or let's say B, then you cannot compute L function composition task in L layers. And a corollary says that for L plus 1 layers, you can, in logarithmic number of parameters.
Okay, so I do have a clarification question.
Okay.
So there was this N1, N2, and so on and so forth. The coordinate of the W's like the sets where the W1, W2 comes from, right? Where do they appear in the theorem?
What was the question again, sorry?
Like, okay, so there was this W1, W2, and so on so forth. They come from sets of size n1, n2, and so on so forth.
Yeah.
Right?
Yeah.
So W is in this big set. Are we putting any constraint on how big or small this set is supposed to be?
No, there's no constraint initially, but the whole proof relies on the fact that they prove that the domain becomes large enough, and then that communication would fail.
So, like, let me ask the question differently. So, if I choose n1, n2, and nl plus 1 all to be equal to 1, I just have one input, then I suppose the theorem will not be true, or is the theorem still true? In that edge case.
So if you are saying that you are just like making all the queries to one input,
Yeah.
and
Yeah.
but still we have all these functions.
Uh-huh.
Yeah, I think if your input is only one, all these functions are applying to only one input, I guess.
So
Then
it's like saying that all the NLs are the same size, they're all of size m.
yeah.
And the theorem still holds in that case. I don't think so. I would guess that it depends on the fact that NL grows with L.
Yeah.
But I don't know. That's for you.
Yeah, so this is what I'm wondering about, really. Because it's like a fine distinction.
Because I think if all of it is one, it can just directly compute it here because there's only one thing it needs to
No,
compute.
there's still other input, which is the
I think, I would think that like, maybe if N1 is, yeah, somehow, like the size of the domain, right? Like this is the size of the domain. Somehow that needs to play at all. Because like if you only have one point in the domain,
Yeah.
then
So basically, the indistinguishable decomposition thing, like for it to hold, they mentioned that there should be a lot of different possibilities of ZL, which is this last function that is getting communicated, and there should
But-
also be a lot of
okay,
different
so
possibilities.
maybe it still holds because you still cannot compute the result of this. There is this computation that we described, this I0 and I1 and I2 and so on and so forth. So if all the W's are the same, they're just like dummy, you still kind of are composing these Z's. And you still have to do that composition, right?
Yeah.
So I really do wonder about the role of this W. They just make the theorem slightly more general by that, and like, then it really doesn't really matter because even in the conditions we don't see these numbers appearing. So I suppose it doesn't matter. But then why don't we prove the theorem just for a case when the W's play no role? It's dummy. Then it's kind of simpler, and it seems to be like a stronger result too.
I suspect that the W does matter because we have L layers of computation, and one way of evaluating this composition would be to take this Z, the last Z, and then compute the composition, right? So if the input was in the reverse order, then we can do everything, right? Like everything becomes easy because you can just compute.
Yeah, but like it's not in the reverse order, right?
But that just depends on the number of layers, right? So if you had, for example, 2 L layers, then the first L levels, the layers, can like reverse the computation.
Uh-huh.
And then the remaining L layers can sort of compute the thing in the proper order, right? So,
Okay.
and the thing that is preventing that happening in this case is the W.
But I saw that the theorem was only true if the number of layers is less than equal to L.
Yeah, right. But so that's the yeah. So I guess the L and L plus 1. But I think the W is really important there. Like the W prevents you from computing the incremental function compositions in sort of one direction. But I don't have like a.
I don't see a solution that would work with L layers that, you know, like for which the theorem doesn't hold. I don't see it.
Yeah, I guess we can work that out.
Also, this indistinguishable decomposition thing, for its own proof, they say that there should be like big number of possible inputs. So if you limit like
How
W's,
big?
then you're basically like restricting the input domain
Sure.
very less. So there are two.
That's the question I'm asking, like, because I didn't see any condition on this numbers in
Yeah.
theorem statement, but that,
So basically the theorem uses indistinguishable decomposition for its proof, and the indistinguishable decomposition in its like inductive proof, they say that there should be a lot of different possibilities of ZL, and there should be a lot of different possibilities of these inputs.
There's a specific theorem that mentions that whenever HDP pitch is like the number of bits that are available, and if they are less than or equal to n raised to power 2 minus 4 L, which is L is like the number of layers, and n is the prompt length of the context length, then it would fail with an n layer transformer. And we did not go into the proof for this, and we're not sure where the numbers actually come from. But this is like one of the theorems that they mention, and this is like the specific numbers if you wanted.
but it's, I still don't see the N1 and N2 and capital L appearing anywhere.
This is the capital L or the number of layers.
Yeah, but like there is N lower index 1 and subscript 2 and so on and so forth. Those were also parameters of the problem. And I don't see those numbers appearing anywhere.
So yeah, again, I was saying that for the indistinguishable decomposition to hold, there should be a lot of different, like this set size, this input set size should be large enough. They call it cover size in the paper. And this ZL, like all the possibilities that we are communicating, it is called the entropy that we are communicating. So the cover size also needs to be large enough, and the entropy also needs to be large enough for the indistinguishable decomposition to hold.
Yes, I guess the question
All right,
was
let's go on
Yeah.
because we're running out of time. I will need to go.
Yeah. Okay. So yeah, I think this was it. Initially, we talked about L function composition non-mathematically. Then we wrote some mathematical stuff about like how this is actually getting computed, and then the autoregressive communication model the authors built to prove lower bound on this L function composition problem. And finally, we talked about the indistinguishable decomposition technique that they use to actually prove that this whole thing
Oh,
in
I
L
feel like
layers.
you're gonna go into that indistinguishability,
Yeah.
the composition thing. You're on?
No.
No,
No. Okay.
Yeah.
All right. Okay.
we are
That's
now
what
just
it
going
is.
to tell the corollaries.
Yeah, we just wanted to have
Okay.
a discussion on the corollaries, and we're almost out of time, so just
Okay.
like
Sure.
one of the main one is that the main theorem says that for L layers, the L function composition would fail, but one of the theorem in corollary is that with L plus 1 layers, just adding one more layer, we can solve the same task with a small transformer or like polylogarithmic number of bits or parameters.
How is that a corollary of the theorem?
I am not sure about that, and I have no idea. And that's why we just left
There are
it
no proofs
late
for
for
the
discussion. And there are no such proofs in the paper. The main chunk of the paper is just the theorem proof for this and its indistinguishable decomposition.
How about the chain of thought one?
Yeah, the chain of thought one says that even with a one layer transformer, we can solve the L function composition task. And basically what it says is that because we are allowed to generate more tokens, not like in this case, we have to just generate the output in like one token. But in chain of thought, we're allowed to generate more tokens. So what we say is that with like chain of thought token 1, we can probably compute fz0 of z1 of z0 in a way, and then with increasing number of chain of thought steps, we can actually just compute the answer to L function composition. But they also say that as the size of function composition increases, so does the steps that we require, and it's basically like the number of like if the domain is n, it increases with the square root of n. So with a domain size of n, the chain of thought steps need to be at least under root of n for that to be able to compute that step.
So it's not linear.
No, it's not
less.
linear, I guess.
Wait, but why? Okay. So first of all, it's surprising it depends on n. Then it's very surprising that it's actually
N
square
here
root
is
n
like
and
the
not
domain of the
linear
function.
n. Like I mean, like square root n is for sure much better, but like where did that come from?
The n here is like the domain of the function, not the context n.
I know. I guess it's like it's some compression thing again. Like birthday paradox somehow brings in this square root n. I don't know what is it. Where is the square root n coming from?
Yeah, not sure.
Like you gotta be doing something really clever, like, or okay. So first of all, why does it need to depend on n? Okay, like because I would have thought that like L steps are gonna do it,
Mm-hmm.
right? Because how would I do it? Well, I would write on the output the result of, I don't know, the last function applied to, like, do the reverse order, right? Like, just do it one step at a time, and then kind of use some counter, like, this is where the output starts, and then from there you're counting back, and like, as long as you see something, then you kind of, like, have this counter thing implemented. And then you just do the compositions one at a time, because the previous result is already written on output, and now you just have to plug that into the previous function, and then you kind of repeat it, and you have to kind of like bridge bigger gaps, but everything's fine. Usually you can do these things in transformers in autoregressive mode. Like we had some ROS exercise, I think, that was talking about how you can do this thing. And so I'm now really wondering about why the size of the domain plays a role in how many steps you're gonna need. I guess in Rasp you are ignoring the details of like how many bits you're gonna need internally to do things, and maybe you don't have enough bits somehow, and then you have to write the output in multiple parts or something. Yeah, I don't know, but it's still like, it's weird, because if it was just like that, then I would expect log n appearing, because that's the number of bits to represent, like numbers in a domain of size n. And okay, so I don't understand at all.
Same.
Okay. So good exercises, homework for everyone.
Project.
Okay, so one of the last things and one of the last qualities that they have is like a comparison between an encoder-based model and a decoder-based model. And for those who do not know how an encoder-based model might work, in decoder we only pay attention to the previous tokens. Like here we can only get information from the previous tokens. But in encoder-based model we do not have that masking. So this L can get information to all the players after that as well. And in that case, it says that while this may not be solvable by a decoder-based model in L layers, an encoder-based model can solve the same task with log L layers. And that's like one of the qualities, and again, they do not have any proof for these qualities mentioned in the paper, so not really sure, but that kind of intuitively makes sense, because that function can pay attention to the parameters over here, then that might be able to compute 4 L layers, and that kind of makes sense. This was all from our side.
Yeah. Those are very fun papers.
Also, thank you to Roshan and Shivam for helping us in reading the paper.
Good. So you guys have any parting thoughts? Where is this going? Is this interesting, useful?
Might be, because in practice we might not know how many functions we want to compute. So if we have like a large enough problem that is complex enough, then probably even in like the normal transformers that we have, we might not be able to solve those tasks right now.
It's not only that the task is somehow big, but computing the result for the task requires kind of sending information in some direction and a lot of information, and then like there could be some general lesson about that, right?
But then again, I'm not sure because the recent transformers are all based on the chain of thought thing. So even though the steps might be large, we might still be able to solve it with enough computation.
Yeah. I mean, there are limits to that too, but different limits. Okay. Yeah. Yeah, one-shot computation is kind of weird. Okay, thank you.